In today's lecture, we discuss tests of statistical significance. These tests use sample data to try and make general conclusions about a population. These are the concepts that we'll discuss in Chapter 22. The reasoning of tests of significance, hypotheses and p-values, statistical significance, calculating p-values, and tests for a population mean. Let's start with an example. People of taste are supposed to prefer fresh brewed coffee to the instant variety, but perhaps many coffee drinkers just need their caffeine fix. A skeptic claims that coffee drinkers can't tell the difference, so let's do an experiment to test this claim. 50 subjects will taste 2 unmarked cups of coffee and say which he or she prefers. 1 cup in each pair contains instant coffee and the other fresh brewed. The statistic that records the results of our experiment is the proportion p hat of the sample who say they like the fresh brewed better. Suppose that we find 36 of our 50 subjects prefer the fresh coffee. In this case, p hat is equal to 36 out of 50, or 72%. For the sake of argument, let's also consider another potential scenario. Suppose only 28 of our 50 subjects like the fresh brewed coffee better. Then our sample proportion would be p hat equal to 28 over 50, or 56%. "72% is stronger evidence against the skeptic's claim than 56%. But how much stronger is it? Furthermore, is 72% in favor convincing enough evidence that the majority of the population prefer fresh coffee? To try and answer these questions, we need a framework. Let's begin by analyzing the skeptic's claim. The skeptic claims that coffee drinkers can't tell fresh from instant, so that only half will choose fresh brewed coffee in a blind taste test. What he is actually claiming is that the population proportion P is equal to 0.5, where P is equal to the proportion of the population which would choose fresh brewed coffee in a blind taste test. Suppose, for the sake of argument, that this claim is true. If this claim were true, and we tested many random samples of 50 coffee drinkers, then the sampling distribution of p hat would follow a normal distribution. This normal distribution would have a mean equal to 0.5 and a standard deviation approximately equal to 0.0707. If this were the case, then how unusual would it be to observe a value of p hat that is 72% or greater? What about 56% or greater? Using Table B, we see that about 20% of samples would produce a value of p hat that is 56% or larger if in fact coffee drinkers can't tell the difference. So about 1 in 5 samples would produce such results. This doesn't seem very out of the ordinary. However, only 0.1% of samples would produce a value of p hat that is 72% or larger if in fact the drinkers can't tell a difference. This seems to be strong evidence against the claim. We can now measure the strength of the evidence against the claim by rephrasing it in terms of probability. If p hat were equal to 0.56, this probability would be the shaded area under the normal curve to the right of 0.56. This area is 0.2. Our sample actually gave p hat equal to 0.72. The probability of getting a sample outcome this large is only about 0.001. The reasoning now is that an outcome that would occur in about 20% of all samples is not strong evidence against the claim. However, an outcome that would only happen about 1 in 1,000 times is good evidence. There are two possible explanations of the fact that 72% of our subjects prefer fresh to instant coffee. The first is that the skeptic is actually correct, and p is equal to 0.5, and by bad luck, we observed a very unlikely outcome. The second is that the population proportion favoring fresh coffee is actually greater than 0.5, so the sample outcome is about what we would expect to observe. Now we cannot be certain that explanation 1 is untrue. Our taste test results could be due to chance alone, but the probability that such a result would occur by chance is so small that we are confident that explanation 2 is correct. In most studies, we hope to show that some definite effect is present in the population. A statistical test begins by supposing for the sake of argument that the effect we seek is not present. We then look for evidence against this claim and in favor of the effect we hope to find. The first step in a test of significance is to state a claim against which we will try to find evidence. This is called the null hypothesis. The claim being tested in a statistical test is called the null hypothesis. The test is designed to assess the strength of the evidence against the null hypothesis. Usually the null hypothesis is a statement of no effect or no difference. The term null hypothesis is abbreviated H lower 0 and is read as H naught. It is a statement about the population and must be stated in terms of a population parameter. On the other hand, the statement we hope or suspect is true is called the alternative hypothesis and it is abbreviated H lower a. A significance test looks for evidence against the null hypothesis and in favor of the alternative. The evidence is strong if the outcome we observe would rarely occur if the null hypothesis is true, and is more probable if the alternative is true. A significance test answers the question by giving a probability. The probability of getting an outcome at least as far as the actually observed outcome from what we would expect when the null hypothesis is true. What counts as far from what we would expect depends on both hypotheses. This probability we are referring to is called the p-value. The probability computed assuming that the null hypothesis is true, that the sample outcome would be as extreme or more extreme than the actually observed outcome is called the p-value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. Let's consider an example. Suppose we wanted to test whether or not a coin was fair. Suppose 4,040 tosses are performed and 2,048 come up heads. The sample proportion of heads is then p hat equal to 0.507. To test whether or not the coin is fair, we need to define the null and alternative hypothesis. What do you think the null hypothesis is? The default position would be that the coin is fair, so that the p is equal to 0.5. If the coin were unfair, then p would be something other than 0.5. With the null and alternative hypotheses defined, we now begin carrying out our test by assuming that the null hypothesis is true. If the null hypothesis is true, the sample proportion of heads has an approximate normal distribution with the following mean and standard deviation. Notice where our observed value of p hat falls relative to the mean. The picture already suggests that this is not an unlikely outcome that would give strong evidence against the claim that p equals 0.5. Recall, the p-value is the probability we would observe something at least as extreme as p hat. These p-values can be visualized as the tail probabilities under a normal curve. In this example, the observations that are at least as extreme as 0.507 are those that are at least 0.007 away from the mean. So the p-value in this case is equal to the sum of the two tail probabilities. Using Table B, we find that the p-value in this example is 0.37. A truly balanced coin would give a result this far or farther from 0.5 about 37% of the time. His results give no reason to think that this coin was not balanced. The alternative hypothesis that p is greater than 0.5 from example 1 is an example of a one-sided alternative. This is because the observations that are inconsistent with the null hypothesis are those that are much larger than 0.5. We are not considering the observations that are much smaller. The alternative that p is not equal to 0.5 from example 2 is an example of a two-sided alternative. This is because the observations that are inconsistent with the null hypothesis are those that are both much larger and much smaller than 0.5. Whether the alternative is one-sided or two-sided determines whether sample results that are extreme in one direction or in both directions count as evidence against the null hypothesis and in favor of the alternative. This also determines whether one tail or two tails will be used to compute the p-value. We can decide in advance how much evidence against the null hypothesis we will insist on. The way to do this is to say, before any data is collected, how small a p-value we will require. The decisive value of p is called the significance level of the test, and is usually denoted with alpha. In general, if the p-value is as small or smaller than alpha, we will say that the data are statistically significant at level alpha. Finding the p-values we gave in the previous examples requires doing normal distribution calculations using Table B. So let's find the p-value from the very first example we looked at on taste testing coffee. If you recall, the null hypothesis was that p equals 0.5, and the alternative was that p was greater than 0.5, where p is the proportion of the population who prefer fresh coffee to instant coffee. If the null hypothesis is true, so that p is equal to 0.5, p hat follows a normal distribution with mean 0.5 and standard deviation 0.0707. According to our sample of 50 people, 36 preferred fresh coffee. So in this case, the sample proportion was 0.72. The alternative hypothesis in this case is one-sided, on the high side. So the p-value is the probability of getting an outcome at least as large as 0.72. Figure 22.1 displays this probability as an area under the normal sampling distribution curve. To find any normal curve probability, move to the standard scale. The standard score for the outcome 0.72 is equal to 3.1, which again is found by subtracting the mean and dividing by the standard deviation. Table B says that the standard score 3.1 is the 99.9 percentile. That is, the area under a normal curve to the left of 3.1 is 0.999. So the area to the right is therefore 0.001, and this is our p-value. Because the p-value is quite small, there is very strong evidence that a majority of the population prefers fresh coffee. The reasoning that leads to significance tests for hypotheses about a population mean mu follows the reasoning that leads to tests about a population proportion. The big idea is to use the sampling distribution that the sample mean would have if the null hypothesis were true. So we locate the value of x bar from our data on this distribution and see how unlikely it is. A value of x bar that would rarely appear if h0 were true is evidence that h0 is not true. The steps are similar to those in tests for a proportion. Let's do an example. The National Center for Health Statistics reports that the mean blood pressure for males 35 to 44 years of age is 128. The medical director for a large company looks at the medical records of 72 executives in this age group and finds that the mean blood pressure in this sample is x bar equal to 126.1 and the standard deviation is 15.2. Is this evidence that the company's executives have a different mean blood pressure from the general population? First, we must define the null and alternative hypotheses. The null hypothesis is no difference from the national mean. The alternative is two-sided because the medical director did not have a particular direction in mind before examining the data. So the hypotheses about the unknown mean mu of the executive population are as follows. If the null hypothesis is true, the sample mean x bar has an approximate normal distribution with mean 128 and standard deviation 15.2 divided by the square root of the sample size, which is about 1.79. Recall the observed sample mean was 126.1. The standard score for this outcome is found by subtracting the mean and dividing by the standard deviation, which is about negative 1.06. Figure 22.5 locates the sample outcome, negative 1.06, on the normal curve that represents the sampling distribution if the null hypothesis is true. The two-sided p-value is the probability of an outcome at least as far out in either direction. This is the shaded area under the curve. To use table B, we'll round the standard score to negative 1.1. This is the 13.57 percentile of a normal distribution. So the area to the left of negative 1.1 is 0.1357. The area to the left of negative 1.1 and to the right of 1.1 is double this, or about 0.27. This is our approximate p-value. If we use software to find the exact value, the p-value is 0.289. Because the p-value is rather large, it gives us no reason to think that the mean blood pressure of the executive population differs from the national average.